In this video, we will talk about impulse functions. In particular, we will look at them as a second-order differential equation is equal to a forcing function where the forcing function is large during a short interval. We also define this integral over here, I of tau, tau being the length of our interval, as negative infinity to infinity, g of t dt, our impulse, our forcing function. And remember, since g of t is equal to 0 everywhere outside of our short interval defined by tau, this integral here, it simplifies to t naught minus t, t naught plus t, g of t dt. Everywhere else outside this interval, it's equal to 0. And this integral here is a measure of strength of the forcing function. In a mechanical system where g of t is a force, the integral is the total impulse of the force over the time interval. Similarly, if y is the current in an electrical circuit and g of t is the time derivative of the voltage, then the integral represents the total voltage impressed on the circuit during the time interval. Next, we will look at the unit impulse function called the Dirac Delta. And the Dirac Delta is defined by these two equations here. That is that the Dirac Delta of t is equal to 0 for t not equal to 0. So the only non-zero portion of the Dirac Delta is at t equals 0. And then the second formula that defines the Dirac Delta is when we integrate from negative infinity to infinity, then we get 1. So for this reason, it's called a unit impulse centered at t equals 0 because t equals 0 is the only place where we have anything non-zero in the function. And it's unit impulse because when we integrate over that interval, we get 1. So this is the Dirac delta. It's centered at 0, but we can look at unit impulses at an arbitrary point centered somewhere other than 0. It's centered at t naught. And we'll be using these formulas here for a Dirac delta centered at t naught, and this would be the corresponding integral. And we'll have examples of this, problems with that where we use these two formulas. Next, we will look at the LaPlace transform for the Dirac delta function. And actually, first we'll look at, the LaPlace transform for the general unit impulse at an arbitrary point, t naught, and that's equal to e to the minus s t naught. And when we're centered at 0, then t naught is equal to 0, and this becomes 1, which is exactly what this form is here. For the Dirac delta, the LaPlace transform of the Dirac delta is equal to 1. Next, we'll solve some differential equations with impulse forcing functions of this form. We find this formula. I've looked up this formula, which will become useful and I looked this up on a table where we have LaPlace transform and the inverse LaPlace transforms. And we'll see examples of how to use this. And then finally, this topic is not in your book, but I believe 1, it's extremely fascinating, and 2, very important. And so I'm just going to state it and then give you a little bit of intuition of why it's true. And the statement is that the Dirac delta function is composed of sines and cosines of all possible frequencies. So in other words, the Dirac delta function contains the entire spectrum of all sines and cosine frequencies. And 1, not only is that amazing, but it ends up being very important. I will not prove this for you, but I'll give you kind of some intuition of why it's true and then also how it's important and how it is used. So we'll back up and go from the beginning and say that we have an impulse phenomena. So we have some phenomena, we have the system modeled by this second-order differential equation, and then we have it equal to g of t. And we're going to say g of t is large during a short time interval. That is for t, time, to be between t naught minus tau and t naught plus tau for some tau greater than 0, and is 0 everywhere else. So it's this impulse right at some centered around time t, that we have some impulse, it's large, everywhere else it's 0. And then we can define this integral here as the integral of tau of g of t from negative infinity to infinity, but since it's 0 everywhere except in this interval, that becomes the integral t naught minus t, t naught plus t of g of t. And this is a measure of strength of this forcing function. In particular, first we're going to look at a g of t that is centered at 0. In other words, t naught is equal to 0. And then g of t is going to be 0, again, when we're outside the interval, where t is less than tau or negative tau, or t is greater than tau. And then we're going to let g of t in this little interval, negative tau to tau, equal 1 over 2 tau. And this will allow us to have our integral equal to 1. And I'll let you take a look at the math here and you can verify that I've done my arithmetic and integrals correctly. And here is the drawing that goes with this definition. Our Dirac delta is equal to 0 everywhere except between negative tau and tau. And then our Dirac delta has a height of 1 over 2 times tau. And you can see also just by this kind of rectangle, if you take the area of the rectangle, you'll see that you would get 1 as our area, as we'd expect from this integral. If we look at as tau gets smaller and smaller, we can see that the height of our Dirac delta function gets larger and larger. So in other words, if tau is spread out over time, the time interval from -8 to 8, then our 1 over 2 tau is equal to 1/16. It's got to be small so that when you integrate, you get 1, or when you take the area under this rectangle, you get 1. Whereas, let's skip over here, when tau is equal to 2, the length of the interval is equal to 4, so that means our 1 over 2 tau is equal to 1/4. So then as we get even smaller, we're going tau equals to 1/2, you see that we have the height here then for this portion of our Dirac delta function is going to equal to 1. And what we want to happen as we take shorter and shorter time intervals for t not equal to 0, so we're not talking about this one point, t equals 0, we're talking everywhere else. So for shorter and shorter time intervals, our delta function here, our Dirac delta, is also going to equal to 0. Again, we're talking about t not equal to 0. So what we want for our idealized Dirac delta function is we want first, as we're going to take smaller and smaller intervals, and as our intervals get smaller, our Dirac delta function is equal to 0. It gets squeezed down to 0. And again, for all t not equal to 0, everything happens at t equals 0. All of a sudden we have this big impulse. But as long as we're not at t equals 0, we want our Dirac delta function to approach 0. And the second thing is we want our integral, at the same time that Dirac delta is approaching 0, our integral from -infinity to infinity should equal to 1. But since we found our integral here is equal to 1, that means the limit as tau approaches 0 is also equal to 1. And I've rewritten those conditions here, and there is no ordinary function at the current that you've currently studied in elementary calculus that satisfies these conditions. So we define our new function called the Dirac delta function, and it's defined by these two conditions here. And this is an example of what is known as a generalized function. So our Dirac delta of t is equal to 0 for all t not equal to 0, and when we integrate our Dirac delta function, it is equal to 1. So again, this is how we're going to define our Dirac delta function. And this is exactly what we defined in our overview slide for the Dirac delta, our two conditions, that the Dirac delta is equal to 0 for t not equal to 0, and then when we integrate the Dirac delta between -infinity and infinity, we get 1, and that is our unit impulse at t equals 0. I will also add that a unit impulse at an arbitrary point, t equals t naught, so instead of centering it at 0, we're going to center at t naught. We'll be using this formula here, and we'll do some examples of this. And the LaPlace transform of our Dirac delta function centered at t naught is equal to e to the minus s t naught. We will be using this formula in my class. I will not be requiring you to know the proof, but I did include it here for your reference. And a quick note, if we're centered at t equals 0, right, so t naught is equal to 0, then this just becomes e to the minus 0, which is just equal to 1. So here's this formula of our Laplace of our Dirac delta function as opposed to a shifted unit impulse. So next we're going to do some example problems of differential equations where we have this impulse function for our forcing function on the right-hand side of the equation. This formula here, I took off of a table of the Laplace transform of functions equals something and also what the inverse Laplace transform is, and it will become useful, so you might want to take a note of that. The first example is to find the solution of the initial value problem 2y double prime plus y prime plus 2y is equal to the Dirac delta t minus 5. And here we have an example where we have shifted our Dirac delta. Our y of 0 is equal to y prime of 0, which is equal to 0. We start by taking the Laplace transform of the left-hand side, which I have done here. So I can, since the Laplace transform is linear, I can pull out the 2. And then Laplace transform of y double prime, I'm using this formula here. And I have our s squared, Laplace transform of f of t minus s f naught minus f prime naught of 0. That's over here. And then I have y prime, which is the Laplace transform of y prime is s f of t minus f naught. And then I have my 2 and my L f of t. I've plugged in my f of 0 and my f prime of 0, so these terms go away, and I'm left with the Laplace transform of f of t times 2s squared plus s plus 2. On the right-hand side of the equation, I'll take the Laplace of the Dirac delta centered at t equals 5, and by our formula here, the Laplace transform will give me e to the minus 5s. Equating the left and the right-hand side of the equation, in other words, equating this with our e to the minus 5s, our right-hand side of the equation, I get the Laplace transform is equal to e to the minus 5s over 2s squared plus s plus 2. I did some algebraic manipulation here. First, I considered my 1 over my denominator, 2s squared plus s plus 2. And you can verify the algebra here, but once I got to this fraction, I pulled out my e to the minus 5s and I put it over 2, and then I kept this portion, my 1 over s plus 1/4 squared plus 15 over 16th. And you can guess why I did this, and that's because I can look up the inverse Laplace of each of these. First, I focus my attention on this portion of my function. So my 1 over s plus 1/4 squared plus 15 over 16. And I see it has this form over here where a is equal to 1/4, right? S minus 1/4 squared, and b is equal to square root of 15 over 4, or over 16. Square root of that would be 4. I do need a b on top, but I can throw in a b, and then I just need to multiply by 4 over square root of 15, like 1 over b over here. So my answer is, again, I'm going to take my b, multiply by the inverse, 4 over square root of 15, e to the at, so that's e to the minus 1/4 t, sine of b of t, square root of 15 over 4t. So I'm just going to make a note. The inverse Laplace transform gives me my function f of lowercase f of t, 4 square root of 15 e to the minus t over 4 sine square root of 15 4 over 4 times t. Now, when I want to get the inverse Laplace transform of the entire function, what I see is I looked up this formula. We'll talk more about where this formula comes from in the next video, but for the sake of being able to do this problem today, I looked up this formula, and that is the inverse Laplace transform of e to the minus cs. That's what we have here. The inverse Laplace transform, the 1/2 we can just pull it out because it's just a scalar multiple and Laplace transform is linear. So we have e to the minus 5s. So here, e to the minus cs, that means c is equal to 5. And then we have this function capital F of s, which we already found with the inverse Laplace transform of capital F of s is this lowercase that we have in this formula here, little f of t of c, which we noted here that f of t is equal to square root 4 square root over 4 over square root of 15e to the minus t to the fourth sine of square root of 15 over 4t. But as you can see, our formula wants f of t minus c. So I made that note. F of t minus 5, remember c is equal to 5, is equal to this expression here. So our inverse Laplace transform is uc of t. And again, here's our u5 of t. I did have to multiply by this 4 square root of 15 and also by this 1/2. So this gives us 2 over square root of 15. And I have uc over t, u5 of t, and then f of t minus c, which I just brought down from here. Since the initial condition at t equals 0 are homogeneous and there's no external excitation till t equals 5, there's no response in the interval between t equals 0 and t equals 5. Then there's an impulse at t equals 5, which is a decaying solution, and you see it's decaying by this exponential here that persists indefinitely, and the response is continuous at t equals 5 despite the singularity in the forcing function. However, the first derivative of the function has a jump discontinuity, and the second derivative has an infinite discontinuity. So in dealing with problems that involve impulsive forcing, the use of the delta function usually simplifies the mathematical calculations significantly. If the actual excitation extends over a short but non-zero time interval, error will be introduced by modeling the excitation as taking place instantaneously. And this error may be negligible, but in practical problems, it should not be dismissed without consideration. Here is another example problem. Find the solution of the initial value problem. Y double prime plus 2y prime plus 2y is equal to Dirac delta t minus pi, where y sub 0 is equal to 1 and y prime of 0 is equal to 0. We start by taking the Laplace transform of both sides of the equation. So this left-hand side, we have the Laplace of y double prime plus 2y prime plus 2y. And using our formulas, here we have the Laplace transform of y double prime up to here. Here we have 2 times the Laplace transform of y prime. And here we have 2 times the Laplace transform of y. So grouping, well, also first plugging in our y naught, so that's f of 0 is equal to 1 on our y prime. This goes away. Here we have 1, and then we can group all of our terms together. So we take out our Laplace transform of f of t, and we group everything else together, and we get s squared plus 2s plus 2 minus s minus 2. Using the formula for our Laplace transform of the Dirac delta function, we can take the Laplace transform of the right-hand side of the equation. So here we see that t naught is equal to pi. So our Laplace transform is e to the minus pi s. Setting the right-hand side equal to the left-hand side. So here I have the Laplace transform of the left-hand side. The Laplace transform of the right-hand side is e to the minus pi over s. So you can see if I solve for the Laplace transform, I'm going to get e to the pi s plus 2 plus s, and then all of that divided by s squared plus 2s plus 2. And I'm just going to divide this into 3 fractions. So I have e to the pi s as my numerator. I have s plus 1 as my numerator, and my 1 as my numerator. And the reason why I divided my s plus 2 as s plus 1 and 1 is because when I do that, when I factor out my denominator, here I have the same thing in my numerator as my denominator, and also here I have the other part of my denominator and my numerator. So these are things I can take the Laplace transform of. And here I have the 2 formulas that I was talking about. So here, because instead of the 2 I have the 1, it can fit this form of my inverse Laplace transform function with my a equal to -1 and my b equal to 1. Right? This form is the same as this. And here I can fit it into this form where a is equal to -1 and b is equal to 1. So I take the inverse Laplace transform first of my 1 over s plus 1 squared plus 1. I take my inverse Laplace transform of my s plus 1 squared over s plus 1 squared plus 1. I'm sorry, this squared shouldn't be there. So before I finish this problem, I just want to back up a bit, and I'm just going to point out that here I have the Laplace transform of 3 terms. But since the Laplace transform is linear, I can take the inverse Laplace transform of each term and then add it together, and I'll get my solution for the inverse Laplace of the sum. So I have my 3 terms. Let's talk about, and this one I'm just going to mention, I had pulled out my e to the minus pi s, so this is times 1 over s plus 1 squared plus 1. We've talked about how to get the inverse Laplace transform of this form because it is exactly this form here with a equals -1 and b equals 1. So our answer is going to be e to the minus 1t, right, cosine of bt, which is just 1t. So this term here, just following it through, is here. Then let's look at this term over here. That follows this form where we have the b is equal to 1, right? And then our a is equal to -1. So the inverse Laplace is going to be e to the minus t sine of t. And that's right over here. We wrote that over here. And just to see, this portion becomes, by the way, this part of our solution, and this over here becomes this part of our solution. But what we still need to work on is this portion of our inverse Laplace transform. And here we use that formula that we looked up on the table that says if we have something of the form e to the minus cs times a function, and that's exactly what we have, where c is equal to pi, e to the minus pi s times some function, then the inverse Laplace of this is going to equal to our step function at c. So in this case, it's going to be our step function mu of pi of t times f of t minus c. This f here is the inverse Laplace of our capital F, this function here. The inverse Laplace of this, it's the same as this yellow one. Here is our inverse Laplace, but now instead of just plugging in t, we need to plug in t minus c. So this will be e to the minus t minus pi, and then sine, and then plugging in t minus pi, and this should be pi, not 1, over here. And this here will be our final answer, our final complete answer. I feel like I should underline this part as well. Our next problem is similar, but not the same. First of all, this left-hand side is different, but that's actually just, that's details. Over here, we have something different, though, because we have our Dirac Delta function times a cosine. And I just rewrote this over here. I don't know why I felt the need to rewrite it. And at this point, I'm going to say we're going to take the inverse Laplace transform of both sides of the equation. Here's the inverse Laplace transform of the left-hand side. Now we come to taking the Laplace transform of the right-hand side. So I have that written here. And I'm looking at this because I'm thinking, oh yeah, this looks like the formula we've been using before with the e to the minus cs, but that's not what this is. So this formula is not going to help us. But we can use our definition of the Laplace transform, which I have written here for your reference because really we defined the Laplace transform a long time ago, like 6 videos ago. So anyway, the Laplace transform of a function is equal to the integral 0 to infinity e to the minus st times the function dt. So we're trying to take the Laplace transform of this, the delta t minus 2 pi cosine of t. So we're going to take the integral 0 to infinity e to the minus st, and then our function dt. And what we are going to use is this form of the integral, which looks sort of like this form of the integral, but one of the things that's different is the limits of integration. But the reason why we want to use this is it's quite convenient. So let me explain how nice this formula is, and then we'll come back to using it in a moment. So when you integrate from negative infinity to infinity, the Dirac delta of t minus t naught, some function f of t dt, remember the Dirac delta is 0 everywhere except at t naught, and at t naught it's equal to 1. So this integral is essentially just going to give you f of t naught. And again, we're using this because it looks incredibly similar to this integral for the Laplace transformation. So I've kept this formula here, but I'm just going to write it out here. And to make it look more like this form, we need to convert the limits of integration. So we're looking here at the problem we want to solve, because we're doing the Laplace transform here. So we have 0 to infinity, e to the minus st, delta t minus 2 pi, cosine of t dt. So we can rewrite this as a function going from infinity to infinity using a step function, this mu of 0, which sets everything before 0 equal to 0. So you can see now that we can convert our Laplace transform integral to something that is of this form, which we can solve with this equation. So I'm going to use that. So when I look at this, again, because of this Dirac delta, everything goes away, everything's 0, except for this impulse function at t equals 2 pi, or t naught equals 2 pi. And so here we have this integral from negative infinity to infinity is of this form, where my t naught is equal to 2 pi, and my little f of t is equal to everything other than our Dirac delta, which is mu naught of t e to the minus st cosine of t, right? So it's just converting this. I can see now I have it in this form. And now I can use my formula. So it's the integral then is equal to f of t naught. So I'm just going to plug in t naught. So I get mu of 0, 2 pi, e to the minus 2 pi s, and cosine of 2 pi. So mu naught at 2 pi is equal to 1, because this is just the step function that's 0, and then when you hit 0, it becomes 1, so everything's 1. Here we have cosine of 2 pi is also equal to 1, so all we're left with is e to the minus 2 pi s. Now I can set the Laplace transform of the left-hand side of my equation equal to the Laplace transform of the right-hand side of my equation. And now I'm on familiar territory, so I have my Laplace transform is equal to e to the minus 2 pi s. I'm going to move the 1 over, plus 1, and then divide by s squared plus 1. I separate this out into two fractions, my 1 over s squared plus 1 and my e to the 2 pi s. I actually pull that out in front and multiply it times 1 times s squared plus 1. I can find my inverse Laplace transform, and then finally, this is my final answer. And now we come to our last topic, which is not in your textbook, but one, I find it incredibly amazing, and two, very important and useful in applications. So I'm just going to take a few minutes to discuss this with you, just to give you a feel or some intuitive feel for it. And the statement is that the Dirac delta function contains or is composed of sines and cosines of all possible frequencies. And I have that written again. A Dirac delta function consists of sines and cosines of all possible frequencies. And why is that significant? Well, since all functions can be written as a sine or cosine series, if we know how a system affects an impulse function, we will know how a system will affect any input function, because this input function can be written in terms of a sine and cosine series. To give you an idea of why this is true, I plotted cosine. I could have done sine, but I chose cosine because it looks more like our delta function centered at 0, and I didn't want to have to deal with shifting. So I used cosine here, and I plotted cosine of x. Here I have cosine of 2x, so twice the frequency, cosine of 3x. And then next, I compared, here's cosine of x. This is cosine of x plus cosine of 2x. So you see it's starting to kind of flatten stuff out, except around 0, it kind of increases the peak, right? The peak for cosine of x was at 1. Now the peak is at 2. When I add cosine of x plus cosine 2x plus cosine of 3x, again, all this other stuff out here, further away from 0, starts to get dampened. And then over here, at 0, we were getting a higher peak. And here I just moved up our summation because I'm not going to show you what cosine of 4x and 5x are. I'm sure you can graph that. By the way, I use Wolfram alpha to make these graphs. So I have cosine of x plus 2x, cosine of x plus cosine 2x plus cosine 3x. Next, I can show you what cosine x plus cosine 2x plus cosine 3x plus cosine 4x. Again, this is starting to dampen, but you can see now our peak here at t equals 0 is starting to get really high, and then cosine 5x, again, all of this here is starting to dampen out. And if you add all the frequencies, and I guess if I wanted to show you what it was, if I added everything up to cosine 10x, I should have written a program to do that for me, but I didn't. But you're welcome to try and see that eventually you get something looking closer and closer like the Dirac Delta function, and if you were able to do all of the frequencies, you would see you would have the Dirac Delta function. I also want to mention, by no means is this a proof of my statement here, because maybe you can actually put in 1,000 and you get this really close Dirac delta, but the thing is there's nothing to say maybe that all of the functions, all the frequencies are in there. Maybe you could have done the same with just maybe the odd frequencies, the 1, 3, and 5, or if you want the even functions, but maybe you could have thrown some out and it would have been okay, like you'd still get the Dirac delta. But it is the case that all frequencies are in the Dirac delta. I'm not going to prove that for you, but I just wanted to give you a sense of how this is working. And also, it's not that surprising that it's going to take a lot of frequencies to make that Dirac delta, because it's a very kind of discontinuous sort of thing. So you'll need like all those high frequencies in there. And the significance of this, again, is if you have a system that you put an input signal in and you want to know what will happen to the output signal. So for example, maybe you have someone playing a guitar and they're in a particular room and you want to know, how does this guitar sound in this room? So what is the output signal? Well, if you can do that by, studying the guitar in the one room. But what if then later you want to put other signals in that you don't know of, but later you want to put other signals in and want to know what will it sound like in this room? Maybe it's a very interesting acoustic space. So what you can do is take an impulse function, run it through the system, and know what the output signal does. And because your impulse function contains all possible frequencies of sines and cosines, then you can know what this room does to all the possible frequencies you can have. So later you can put in any system and you don't even have to have the room anymore. You'll know what happens to that system to that signal when you put it through the system, because you can decompose your signal into a series of sines and cosine series of different frequencies, and you know how this system will affect each frequency. To review what we've discussed in this video, we talked about impulse functions. We looked at impulse functions where they were the forcing function of a system with a second order differential equation. And this forcing function, we said, was an impulse function. In other words, it was large during a short interval, which we said was centered around t naught, or t, and its length was tau on each side of t. We looked at this integral here, which is negative infinity to infinity of our forcing function, which in this case is a forcing impulse function. And then because the impulse function is 0 everywhere except in this small interval, then the limits of integration become t naught minus tau, t naught plus tau. And we said this integral is a measure of the strength of the forcing function. In a mechanical system where g of t is a force, the integral is the total impulse of the force over the time interval. Next, we looked at the Dirac delta and also unit impulse functions. So the Dirac delta was in particular a unit impulse function that we defined with these two formulas. First, we said it's equal to 0 for all t not equal to 0. So everything happens at t equals 0. But before anything outside of t equals 0 is 0. And then the integral from negative infinity to infinity is equal to 1. So in other words, the strength of the total impulse of the Dirac delta is equal to 1. So that's a unit impulse at t equals 0. We did talk about unit impulses that are centered other places other than 0 at t naught, and we use these formulas here for those unit impulses set at an arbitrary point or centered at an arbitrary point. Next, we define the LaPlace transform of these unit impulse functions, and it's equal to e to the minus s t naught, where t naught is where it's centered. And if t naught is equal to 0, if it's the Dirac delta, then we have t naught is equal to 0, so the LaPlace transform becomes 1. So the LaPlace transform of the Dirac delta is equal to 1. We solved several differential equations with an impulse forcing function. And we used this formula here from a table of inverse Laplace transforms. Finally, I talked about the Dirac delta function and the fact that it contains or is composed of all of sines and cosines of all possible frequencies, and I gave you kind of an idea of why that was true and also why it's important, essentially because any function can be written as a series of sines and cosines. Just you have different coefficients in front of each sine and cosine of different frequencies. But since you can write that as frequencies, then if you send an impulse function through a system, you will know how that impulse function affects all possible frequencies. So then if you have a signal with just a few frequencies, you can know what the response of the system is going to be. So that's it. Oh, and we will look at this a little more also in our next video. But that's it for this video. Thank you for watching.